Well, hi. It's a Tuesday evening, and this must be a ham radio upgrade class, a class that is for those who have your amateur radio license in the United States, the general or advanced class, or if you're trying to take all three tests at once, which our student Tim is. Good luck, man. I'm Gary, your instructor tonight, ham radio call sign Whiskey 4 Echo Echo Yankee, and we work out of this book, the American Radio Relay League License Manual for the extra class, the green book here, and it's the 13th edition. This is the one you want to get to follow along, and we're halfway through the class at least. We're up to chapter 7, but before we get started on that, I've got some not good news and some nice news. Let's start out with the not good news, and for many who have been participating in our classes, this class and other classes, we have a student, the perennial student, Charlie. You might recognize him as the gentleman who's been sitting in a hospital bed, either actually in a hospital or back at home. Well, I got an email this afternoon from his good friend Marshall, who told me that unfortunately Charlie passed away last week. Charlie was an interesting guy. He had my phone number, he had Dave's phone number, and he would call and he would ask questions, and they were good questions, and it caused me to think and to make sure that I could explain something. He was always, no matter his medical issues and whatnot, he was always upbeat and working on projects, thinking about things that he wanted to do, and so he made me a better instructor. And so, Charlie, we're going to miss you, but we'll see you on the other side. And yeah, he was in this class. I think he was in this class last week. I can't remember for sure. He was watching sometimes on YouTube and sometimes in the Zoom classroom. But Charlie, ham call sign Kilo Charlie 2 Sierra Tango Oscar. And you can look him up on QRZ. Here is his family's address if you wanted to send a condolence card. I'm sure they would appreciate it. And yeah, Charlie, we're going to miss you. So obviously that's the sad part of the news for tonight. The happy part of the news for the night, let me get my, hang on, there it is. Can't see my cursor. All right, if I start that, all right. Now if you go back to the laptop, you'll see this weekend was the CQ Worldwide Single Sideband DX contest. I mentioned a little bit about it last week. Dave operated in it, Bruce operated in it, and I operated in it, but I'm the crazy one in this case. It's a 48-hour contest, Saturday and Sunday, UTC time. I've been operating in the contest for a number of years. This is my favorite. And I had a personal goal that I wanted to break the 1,000,000-point barrier. That's what I wanted to do. And you get points for making contacts, and then for working CQ zones, which are multipliers, and then working new countries or other countries. And so the combination of those things, contacts, zones, and countries, you multiply it together. And I wanted to break through the 1,000,000-point barrier. Interestingly, last year I made more contacts than I did this year, but I scored less. But I did it. I made it to 1,042,851 points in the contest. I couldn't have done it without the help of Bruce, who helped me get up antennas for 160 meters and 80 meters. It was just a heck of a lot of fun. If you're a glutton for punishment, I don't recommend it, but I do it just for memory's sake and for those who couldn't participate in the contest. I'm putting videos up of my entire 24 hours in the chair working the contest. It's not super exciting, but you might find it interesting. So if you just look on my YouTube channel, look for the playlist, CQ Worldwide SSB 2025. I've got 6 videos up right now. There's going to probably be a total of 18. I warned you. But anyway, we made it to the million. I'm so happy about that. All right, here we go. Chapter 7 tonight, radio measurements and performance. And we have people getting into our classes. Some have taken our technician class, and some have taken our general class, and then they come here into the extra class. Others just kind of jump into the extra class. And so I just want to make sure we've all got a common baseline. So I kind of want to do a waveform review just to bring us all up to speed. All right, DC, direct current, DC is DC. It's here on the screen. Let me turn on my laser pointer. Boom. We have time.
That's asystole.
What is that?
That's asystole in medicine.
Okay.
Unstable waveform. It means you're dead.
Oh no!
Or your leads are off.
Ah, there we go. All right. Well, anyway, in this case, we have a constant voltage. This looks like 250 volts or thereabouts over time. So this is DC voltage. So we have DC voltage in amateur radio, but we also have AC, alternating current voltage, alternating from a positive swing back down to 0 into a negative area, back to 0, and so on and so forth. And this is a sine wave. Sine wave is generated either electronically using an oscillator stage, or it can be generated mechanically rotationally by using a generator. House power that we power our gear from is a 60 cycle alternating current. Here's another view looking at the sine wave and how it corresponds to the points on a compass, 0 degrees, 90 degrees, 270 degrees, etc. So 180 degrees, I think I left that out there. But anyway, so we're going to take some audio here, Bruce. Let's take a listen here to a little video demo from my workshop with regards to a sine wave. So here we are in the workshop. This is our first test setup. We have the generator, which is right here on the left-hand side, set up for a 500 kilohertz sine wave, and it is feeding both my oscilloscope, you can see the sine wave, and the spectrum analyzer. And you can see on the spectrum analyzer the left-handmost blip going up there with the marker. That's the primary signal for the sine wave. And any harmonics, which are indicated by the subsequent markers, are very down, 60 dB below that carrier level. So a sine wave is essentially a single frequency output. So in the oscilloscope, and then what we're seeing here is in the time domain, we're looking at amplitude on the vertical scale and time on the horizontal scale, whereas in the spectrum analyzer, the tiny SA that you saw there, it was in the frequency domain. And some of the measurements we make in the time domain are amplitude, frequency, and period. Period is the time it takes in seconds or milliseconds or microseconds to complete one cycle. Knowing the period and knowing that the radio waves travel at the speed of light, we can then calculate the wavelength. And that's where the little pyramid formula from 300 divided by the frequency in megahertz will give you the wavelength in meters, or the 300 divided by the wavelength in meters will give you the frequency in megahertz, something that we teach even in the technician class. And sine wave amplitude measurements, we can look at the peak value, or we can look at the peak-to-peak value. RMS voltage is an interesting thing. It's the DC equivalent. It's the equivalent work power that an AC signal might have. And that's, if it's a sine wave, it's 0.707 times the peak value. It will give you the RMS voltage, the equivalent to what a DC voltage would be to heat up something. RMS is the heating effect, so it's the same. Now, why would we want to do that? Well, it actually has some practical applications. Here's the definition of RMS, root mean squared, and if you want to go through it, and you can understand all of it. But we use it to measure the power of a complex waveform. We can use it to measure the power of a sine wave, but also a non-sinusoidal waveform. And we do that, again, by measuring heat. So if we have a DC source and it heats the resistor here up to a certain temperature, if we have an AC source and we heat it to exactly the same temperature as measured by our gauge here, then we know that the RMS value of this is the same as the DC value of this. And we used to use this in Voice of America to measure the power output of our high-powered shortwave transmitters. This is a Marconi B6128, and we would actually run the output of the transmitter through coax down into a load here, and we would pump a slurry mixture to cool that at a certain rate, and we would measure the rise and fall of temperature on a gauge, and that would was properly calibrated would tell us that we're getting 500,000 watts out of the transmitter. The transmitter was performing whether it was modulated or unmodulated. So that would help us to know if we had an output problem, for example, on a transmitter. Now, of course, you don't need a dummy load like this. What you probably will find is a dummy load like this. The Heath Cantenna was a 50 ohm non-inductive resistor inside of a paint can filled with mineral oil and to cool it off. Same thing that we did in VOA, and you can actually, if you wanted to measure the temperature rise, these things will get hot and calculate out what the actual output power would be. We don't deal with it very much, but the average voltage or current, it's a periodic waveform that deals with the area under the sine wave. So I put it in here for completeness, but it's not something that we deal with a lot. Now, we do deal with in phase and out of phase, or in phase and quadrature phase signals. These are signals that are 90 degrees apart, and in this case we have two sine waves. And they're 90 degrees and time shifted with each other. And with these in phase and quadrature signals, I and Q, well, it doesn't have to be a sine wave. It could be a complex wave. And other waveforms that we deal with are square waves, triangle waves, and sawtooth waves. But these complex waves are actually made up of sine waves. And we know this through the process of Fourier analysis. It proves that complex waveforms can be made up of multiple sine waves. And I and Q provides us with a way of generating some of these. So a square wave, you see it here, kind of blocky, flat top going down, flat on the bottom coming up. This is a square wave. A square wave is made up of a sine wave at a fundamental frequency plus all of its odd harmonics. And I love this GIF, this animation here. So here we have the fundamental frequency up here, all right? And here's the third harmonic, which is an odd harmonic, the fifth harmonic, yes, and the seventh harmonic. And when they're added together like this, you can see it's starting to approach a square wave. And notice it's a wheel within a wheel within a wheel. And so this is one proof of the concept. Another, we can do an analysis, again, using the oscilloscope and the spectrum analyzer. Next up, we set the generator to a square wave output. And you can see over on the oscilloscope here, yes, indeed, it is a square wave. And if we look at the tiny spectrum analyzer, you can see that the primary outputs are the odd harmonics. So my setup there isn't perfect. We had some even harmonics coming through, but you get the idea. So a triangle wave is another version of a complex waveform. Here you see an animation. It uses, again, an odd harmonics with a roll-off, a frequency roll-off that is different than that with a square wave. And so again, here we have a diagram of the time domain up here on the top and frequency domain on the bottom, and I was able to recreate it downstairs in the workshop. Now we set the generator to output a 500 kilohertz triangle wave. And if we pan over to the oscilloscope, you can see indeed it is a triangle wave. And if we look to the tiny spectrum analyzer, you can see that it has odd harmonics as the main components. And moving on, the sawtooth wave. The rise time and fall times are different. You can see it's got a gradual, in this case, rise time and a very abrupt fall time. This is made up of a sine wave plus all harmonics, not just the odd harmonics, but also the even harmonics as well. And you can see here in this animation, we start out with a fundamental, add the second, third, fourth, and builds, we're now up to the 38th harmonic, whatever. You build up to a sawtooth wave. And yes, I did it again down in the workshop. And now we have the generator set to output a sawtooth wave. And you can see what it looks like in the time domain on the oscilloscope. And on the tiny spectrum analyzer, we can see that its components are the fundamental plus all of the harmonics. So we've been looking at waveforms and complex waveforms. We want to move ahead to modulated signals. The basis for radio, we have a very high frequency radio carrier, audio modulation, if it's going to be a voice signal, for example, and we can vary the amplitude or the power of that signal in time with the audio. That's amplitude modulation. Or we can vary the frequency in time with the audio, and that's frequency modulation. Now, transmitted output power with an unmodulated sine wave, for whatever reason, they call it average power. And so you calculate using the power formula with the RMS voltages for voltage and current. You'll see this maybe as we move on ahead here. Here's an example of amplitude modulation. You can see the audio on the bottom and the modulated RF carrier up at the top. Now, this is an AM signal, which contains a lower sideband, an upper sideband, and the carrier signal. We primarily transmit single sideband on HF, for example, although there still is some AM signals to be had out there. But we talk about, with single sideband, we talk about the peak envelope power. And what the peak envelope power is, if you look on a waveform monitor, an oscilloscope, and you see the peak level of RF output, the modulated output. And remember, with a single sideband signal, if you don't talk, there is no output power. But when you talk, then you'll get this sort of a waveform. And if you take that value, the peak value, and then multiply that by 0.707, you can use that to calculate the peak envelope power. And peak envelope power is typically 2.5 times the average power of an unmodulated carrier. It's in blue, so that might be important. And voice processing will increase the average output power of a modulated signal. And what determines the output power? Well, it's the characteristics of the modulating signal. So, here we've got one that is nice, cleanly modulated. Here we've got some speech processing added. These are what they call trapezoidal waveforms. So to calculate the modulated signal power, again, we use the peak envelope voltage, and we multiply that by 0.707 to get an RMS equivalent. We square that, and then we divide it by the impedance, typically 50 ohms in our system. So that's how peak envelope power can be calculated, and if you have a dummy load, for example, and you can measure the voltages on a waveform monitor or oscilloscope, then you'll be able to do this calculation. All right, so that was my waveform review. Let's go ahead and get started in section 7.1, dealing with test equipment. And the very first piece of test equipment you probably ever bought was a multimeter. Whether it was an analog multimeter like I got when I was 16 years old, or a digital multimeter, there are three things that you want to consider. The accuracy of the meter, and that has to do with, is the meter calibrated to a standard, a known good value? How precise are the measurements that you're making? It has to do with the markings on a scale or the number of digits in a digital meter. And then the resolution is the smallest difference that can be accurately distinguished? That's not the, is that the right word? Okay. I bought one of these, and I kind of like it. And it's changed to hands. I believe they're still in Wake Forest, North Carolina. But this is a DVM calibrator, digital voltmeter calibrator. It has both frequency and voltage standards built in. It's just a little device, and you can use it to whatever multimeter you have to calibrate it. It's got precision resistors as a resistance source. And let me give you a little demo here of some multimeters down in the workshop using the DVM. I wanted to demonstrate the difference between an RMS measuring AC voltmeter and a non-RMS meter. And you can do that using my digital multimeter calibrator here. And at the moment, the calibrator is connected up to my oscilloscope, which, if we look closely, it's a square wave. And it's a plus 5 volts and minus 5 volts with a 50% duty cycle. And the equivalent DC of that would be 5 volts on all the time. So now I've turned the lights on so you can see the meters a little better. This is my Beckman digital voltmeter from about the 1990s. And on the AC scale, you can see it's reading 5.4 volts AC. And now in contrast, I've hooked up my newer Chinese true RMS meter. And you notice that it is reading 4.969 volts, and you can maybe read the frequency readout above of 99 hertz. This is more accurate. The RMS value should have been 5 volts. It's 4.96. That's pretty close, but there are adjustments inside a meter where you could calibrate it to be exactly 5 volts. So when you're using a meter, here's the observer effect. The act of observing influences the phenomenon being observed. And this is nowhere more apparent than if you're using an older analog voltmeter. Older analog meters have a rating of ohms per volt. So just putting your meter across a device, a resistor, for example, in a circuit, you're providing an alternate path for current to flow. And old analog meters, their ohms per volt reading, my first meter that I had was a 20,000 ohm per volt meter. And what that means is that if I was on the 10 volt scale, full scale, 10 volts, and it's 20,000 ohms per volt, then the meter's impedance would be 200,000 ohms. It'd be the equivalent of putting a 200,000 ohm resistor across the circuit that you're trying to test. That was important, especially back in the day of vacuum tubes, because vacuum tubes could be thrown off by a resistance that seems fairly high, but it's not. And so the biases and everything else could be changed such that if you were doing for example, television servicing and things like that, and you've got schematic diagrams from Sam's Photofax, anybody remember those, that they would list on the schematics what they'd have voltages around the circuit, but they'd tell you what kind of meter they were using, because you had to keep that in mind. If they were using a particular meter and you didn't have one that had the same ohms per volt reading, you might get a different value. It's all about how much does the meter load down the circuit. And you can see here this circuit diagram. We have a 50 microamp meter, 50 microamps full scale here, and we have various resistors ahead of it to give it a different voltage readings. So 1 volt, 10 volts, 100 volts. So this meter would have 15,000 ohm per 1 volt. That would be this meter's rating. Let's look down in the shop. I got a collection of meters down there. Let's see how these two compare. I want to demonstrate the concept of ohms per volt using this small snap-it analog meter. It's set on the DC volts and 2.5 volt scale. This little meter is rated at 10,000 ohms per volt. So 2.5 times 10,000 actually gives you a loading of 25,000 ohms as measured on my meter here to the right. We're actually connected from positive to positive, negative to negative, and reading the resistors inside the meter. 25,000 ohms would load down a circuit considerably. So this is something that a technician has to keep in mind. If we go to the 50 volt scale on the little snap-it meter, 50 times 10,000 is 500,000 or 0.5 mega ohms as indicated on the digital meter. And if we go up to the 250 volt scale, it's 2.5 mega ohms. So this is a meter with 10,000 ohms per volt. A lot of meters that were sold with 20,000 ohms per volt or 30,000 ohms per volt, they would load the circuit less. But the best is a vacuum tube voltmeter or modern digital voltmeters, which have a 1 mega ohm or greater input impedance that does not load the circuit down. So vacuum tube voltmeters, they were the next thing to come along, using vacuum tubes on the input stage. They actually have an input impedance of 11 mega ohms because they have a 10 mega ohm resistor in the probe. So this would not load down a circuit as much and would give you more accurate voltage readings in tube type circuits and things like that. All right. Other kinds of test equipment you might want to be aware of. Grid dip meters. This is an old Millen unit, but there are other types as well. They're used to find the resonant frequency of an LC circuit. And you actually have these coils in the case here, which would plug into the end of the meter up here. And then you would bring it close to an tuned circuit, like in your linear amplifier. If you wanted to know where that circuit was tuned, and you'd watch the meter down here. And it's got a vacuum tube amplifier inside, and when you get actually, and you adjust with a knob over here the frequency, and when you get to the frequency that the circuit is resonant at, it will couple energy into that circuit, and you will see the deflection on the grid dip meter. But if you were too tightly coupled or too close, you could get an inaccurate reading. But you would not believe the number of radio circuits and equipment and whatnot that were fixed and troubleshooting with just a simple piece of test equipment like this grid dip meter. You'll find them at Hamfests. Whether you should get one or not, I don't know. But you want to know what they are. Also at Hamfest, you'll see a lot of these component impedance bridges, and it's a balanced bridge, and you have terminals up here that you put your unknown device, capacitor, resistor, inductor, or whatever, and you adjust the knobs to get a balance or a null here on the meter. And then you can read values off of the scales here that will tell you what that device is. It's inductance, capacitance, or resistance. It'll give a very precise null when you get it all tuned up. Now, a derivation of this that came along that helped hams tune antennas was something called an RF circuit bridge, which used an RF generator through a coupling here into a bridge circuit, as you see here, and you'd have an unknown connection. You can maybe even put an antenna there, and you'd have two adjustable devices, in this case capacitors, one here for reactance and one here for resistance, and it would then tell you what the antenna's series resistance and complex reactance was, so you can calculate the complex impedance. That's an RF circuit bridge. These have largely been superseded, but I want to give you the background. Noise bridges were the next thing. Remember, this used an RF signal generator as a source. Well, noise is wideband energy, and so if you could use noise as your source and use a radio as the detector, then you could adjust the bridge here for an absence of signal or a null in the noise. And when you did that, then you could read the values off the front here for resistance and reactance. Now, I said these have been largely superseded by these antenna analyzers. This is the classic MFJ 259, which again has various frequency ranges. It has a built-in RF generator. It'll tell you standing wave ratio based on whatever reference impedance you say. It'll give you the complex impedance magnitude here, and then it'll give you the more detailed information about series R and series X up here on the digital display. I don't have one of these, but I do have one of these. This is a Rig Expert AA54, and it uses something similar, but it can also then do graphs and charts to tell you where your particular antenna might be resonant or the impedance matches. So also note, don't buy these on eBay. Buy them from a reputable dealer, because the front end of these can be blown out by static, or never run your transmitter into one of these. That's not what this is all about. You'll blow the front end for sure. And a lot of people, unscrupulous, will sell blown out units on eBay. So buy from a reputable dealer. And Rig Expert also has software that goes with their devices, so that you can actually do Smith charts and other complex analysis using these very simple, relatively simple antenna analyzers. We'll talk more about the Smith chart yet to come. Not tonight, but in the future. All right. More test equipment, frequency counters. This is just to tell you if you've got an unknown signal and you want to know what its frequency is, or you've got a transmitter and you want to see if it's on frequency, you use one of these, a frequency counter. Now, you can buy inexpensive ones, or you can buy very expensive lab-grade instruments, and the whole difference is this: the time-based accuracy of the unit. It's measured in parts per million, and the expensive ones are the most accurate. Stability is also indicated in parts per million, and the typical input impedance of one of these is about a mega ohm. So if you're going to run a transmitter into it, you've got to provide an attenuator and a 50 ohm load ahead of it, so you don't blow out the front end of the frequency counter. So this measures the frequency in hertz or kilohertz or megahertz, and sometimes on these meters you will also have a button that is a period counter. So remember, period is the inverse of frequency. It's better resolution for very low frequency signals, audio signals, etc. So that's what you might want to use if you're using a very low frequency signal, is use a period counter. I have a monitor that is flashing over here that I don't know why. Okay. before, if you have an inexpensive frequency counter, it may only be rated for use up to, say, 100 megahertz. But I want to measure the output of my HT and see if my HT is on frequency in the 2 meter band. That's above 100 megahertz. How can I do that? Well, you can go to a hamfest and look for one of these, a prescaler. A prescaler increases a frequency counter's frequency range by dividing the frequency of an incoming signal by a known factor, typically 10. So your 140 megahertz 2 meter frequency would read about 14 megahertz. And so a prescaler can allow you to increase the frequency range of a frequency counter. We've talked about oscilloscopes earlier. You saw down in my workshop. You have analog oscilloscopes, which are all analog devices. The signal comes in, it's amplified, it has DC amplifiers, and these are rated up to 50 megahertz or 100 megahertz. Then you have digital storage oscilloscopes, which can do much of the same thing, but they can have multiple additional inputs. It can store waveforms. It can do Fourier transforms that'll turn it from a time domain device into a frequency domain device. So oscilloscopes, their basic thing is to measure amplitude versus time. And for complex waveforms, that's what you need. You're looking in the time domain. There are various controls that control the sensitivity, the time base division on the horizontal scale, triggering when the trace starts, and it displays amplitude at different times. And complex waveforms like television video signals, for example, that's what you need in order to find out what's going on with those. Now I mentioned triggering, which is when the trace starts. And a lot of scopes will have a triggering input, which you can use, or you can trigger off one of the A input or B input, and you can adjust the triggering to A or B or to an external input. One of the things you can set it to is the line input. And the line input is all about 60 hertz power. It actually is triggering the oscilloscope based on the power from your socket on the wall. Why would you want to do that? Well, if you're working on analog power supplies, that's the way you can get a very stable display to look for power supply ripple. So you can see what the amplitude, how well your filter capacitors are doing, and whether they might be going or whether you need to add some more. So that's line triggering for an oscilloscope. As important as the oscilloscope is, are the probes that you use. You always want to keep the ground lead in an oscilloscope probe as short as possible. So look at this little guy right here. That's about right. That's about all you want. The scope probes have to match the oscilloscope, the scope's input impedance. Typically, it'll have a voltage divider inside at times 10. It'll be a low capacitance probe, and it will have a rated bandwidth. And the probe's rated bandwidth has to be at least that equal to the scope's bandwidth. So you don't want to have a 500 hertz or 500 megahertz scope and a 100 megahertz probe, because you'll get inaccurate readings above 100 megahertz. And no matter you go through a process of probe compensation, no matter which oscilloscope probe you have, and this adjustment right here, it's built into the scope probe, and it adjusts the equalization, the frequency response of the probe to be flat. And so when you have a properly adjusted probe, you'll get a square wave. You actually hook the probe up to a test output on the scope. This is properly adjusted. This is misadjusted in one direction. This is misadjusted in the opposite direction. Well, I was in the workshop. Let's try. So I want to talk through the process of probe compensation on an oscilloscope. Here I have my Rigel oscilloscope on, and the probe is connected to a calibration output here in the right corner. And you can see the square wave on the screen, and you can also see that the square wave leading edge is peaked. That's not what it's supposed to look like. It's supposed to be a square wave. The probe is in the times 10 position. You can only make this adjustment when it's in the times 10 position. And you have a little tool that scope manufacturers send you, or you can use a little alignment tool. It's just a small piece of metal held in a plastic holder so you don't get too much stray capacitance down near the control. And by adjusting the variable capacitor that's on the scope probe, see there, it's squared up. If I go too far, you'll see the leading edge becomes rounded. That's no good either. So you want to adjust it until your square wave is square. Yeah, so there you go. And digital oscilloscopes have some advantages. There is an analog to digital converter at each of the channel inputs. The sample rate, we talked about that in the past, that's critical. It determines the scope's bandwidth. Remember, if you got too slow or too low a sample rate and you feed in a high frequency signal, a higher frequency signal, you're going to get false signals, aliases. Same thing applies, the Nyquist theorem. Now, a nice thing about the digital scope is it can write the waveform to memory so you can have it for later analysis. Now, digital scopes typically have automatic frequency and amplitude digital readout. So right up here you can actually read values. There's storage of waveforms for future reference. And there's a manipulation of the time base on a captured waveform. So you can go back and look at the memory and then readjust things and get a clearer look. Notice there's 3 things here. I wonder what that might mean. All right. And if you'd like to play with an oscilloscope, but you don't want to buy one necessarily, but if you've got a computer with a sound card, then I'd suggest you try a sound card oscilloscope. It uses your audio card's sample rate, so 44 kilohertz or 44 kilobits per second or 48 kilobits per second. You're only going to be dealing with audio with a sound card oscilloscope, because the sample rate again must be at least 2 times the highest frequency to be measured. But here in Europe, we are actually using one of these right now to monitor the phase of my microphone signal, because we've had problems with out-of-phase signals. It's a practical device that you can use. So sound card oscilloscope, you can go there. It's free. Although if you use it regularly like we did, we made a donation. Not an oscilloscope, but kinda. A logic analyzer, where oscilloscopes maybe have 2 inputs or 4 inputs. A logic analyzer could have 64 inputs or 128 inputs, and you can display multiple digital states. So we're looking at digital signals simultaneously. The whole point with this logic analyzer is to look at the relationships between the inputs and outputs of gates. The inputs and outputs, if it's a NOR gate or an OR gate or whatnot, are they triggering properly? For a circuit analysis, a logic analyzer can be very invaluable. And for radio frequency work, we always like to have a spectrum analyzer, whether it be the little tiny spectrum analyzer that you saw down in my workshop, which is a viable analyzer, but not as good as this one. This is a Hewlett-Packard. A spectrum analyzer views signals in the frequency domain, not the time domain. So the scale is amplitude on the vertical axis and frequency on the horizontal axis. And it displays signal bandwidth or distortion products. It's calibrated in amplitude directly into dBm, so you can make repeatable measurements. You can have input filtering to IEEE standards, but the input on the device is very sensitive. So you have to keep your input levels on this one or on my tiny SA, you have to keep them down, and you can use attenuators. Here's one if you want to measure the output of a transmitter. This is a high power RF attenuator, and this would then protect the spectrum analyzer input and also then allow you to make measurements. And these will have an attenuation rating, 20, 30, 40 dB, something like that. Another thing the spectrum analyzer can do is, if you're looking in this frequency domain, is you can use something called the two-tone test. in this case, we do this with amateur radio transmitters. You modulate the transmitter with two non-harmonically related audio tones. So 1,000 hertz and 1,500 hertz would be fine. 1,000 hertz and 2,000 hertz, no good. That's because the 2,000 is a harmonic of 1,000. So two non-harmonically related audio tones, and you can then measure the distortion products, these things over here, on the spectrum analyzer, and make sure that your amplifier or your transmitter is as linear as possible. So I just provide this link. This is the Tiny SA. This is the device that we saw down below. It's a poor man's spectrum analyzer. It doesn't cost $20,000, $30,000. It's about $150 to $200, and very handy to play with and to learn things about RF. All right, here's some questions. Let's see how we did. So which of the following limits the highest frequency signal that can be accurately displayed on a digital oscilloscope?
Alpha.
See that? He said alpha, yep, the sampling rate of the analog to digital converter. And which of the following parameters does a spectrum analyzer display on the vertical and horizontal axes? Speak up, please.
Bravo.
Yes, bravo. Yes, signal amplitude on the vertical and frequency on the horizontal. That's a spectrum analyzer. And which of the following test instruments is used to display spurious signals and/or intermodulation distortion products generated by a single sideband transmitter?
Bravo.
Yep, that's the spectrum analyzer. And how is compensation of an oscilloscope probe performed?
Alpha.
Alpha.
Indeed. The square wave is displayed by connecting the probe to a test point, and the probe is adjusted until the horizontal portions are nearly as flat as possible. And what is the purpose of using a prescaler with a frequency counter?
No.
I think I heard it. Not Bravo.
Delta.
It is delta. You're reducing the signal frequency by scaling it down to within the counter's operating range. And what is the effect of aliasing on a digital oscilloscope when displaying a waveform?
Alpha.
Alpha.
We saw that with Dave's presentations. It's a false low-frequency version of the waveform. And which of the following is good practice when using an oscilloscope probe?
Alpha.
Alpha.
Yeah, you want to minimize the length of the probe's ground connection. And which trigger mode is most effective when using an oscilloscope to measure a linear power supply's output ripple?
Delta.
Delta, line triggering. And which of the following factors most affects the accuracy of a frequency counter?
Bravo.
Yeah, it's built into it is time-based accuracy. And what is the significance of voltmeter sensitivity expressed in ohms per volt?
Alpha.
So you take the full scale reading of the voltmeter on the 10 volt scale, let's say, multiplied by its ohms per volt rating. That is the input impedance then of the voltmeter. And which of the following methods measures intermodulation distortion in a single sideband transmitter? i.e. the two-tone test.
Alpha.
Alpha.
Not alpha.
No.
Bravo. Bravo.
You're modulating the transmitter with audio frequency signals. So you modulate the transmitter using two audio frequency signals having non-harmonically related frequencies, and then you observe the RF output on a spectrum analyzer. So Bravo is the proper answer here.
Dirty wording. Yep.
They're tricky. So what techniques shows that a square wave is made up of a sine wave and its odd harmonics? How do we know this?
Alpha.
Through Mr. Fourier, yes, Fourier analysis. And which of the following describes a signal in the time domain?
Bravo.
Yes, bravo. Amplitude at different times, over different times. And what is the benefit of making voltage measurements with a true RMS calculating meter?
Delta.
Delta.
Yes, the RMS measurement is measured for both sinusoidal sine waves and complex or non-sinusoidal signals like a modulated RF transmitter. So what is the approximate ratio of peak envelope power, PEP, to average power in an unprocessed single sideband phone signal? Do you remember?
Yep. Alpha.
Alpha.
2.5 to 1. And what determines the PEP to average power ratio of an unprocessed single sideband phone signal? What is the,
Bravo.
yeah, the greatest characteristic, the speech characteristics has the greatest impact. All right, you hung in there, you did great. We're at the intermission. So let's get up
Yay.
and move around. We've got 5 minutes, and we'll come on back and we'll continue with receiver performance. And we are back. Hope you get a chance to get up and move around and stretch a little bit. So I think we've got 2 more sections to go before we are done tonight. And we're going to get started with section 7.2, talking about receiver performance. And one thing about receivers is you can't get an amplifier to make them better. Well, okay, that's my next slide. But you can't work them if you can't hear them. That's what I was trying to say. If you can't work a station, then you got a problem. So you have to have a receiver that's sensitive, and you have to have one that's selective, that can discriminate. And some older radios, like the Collins and whatnot, are surprisingly good even today. We'll talk to you about why that is. This is what I was pointing out. You can increase your power by adding a linear amplifier, but there is no such thing as a receive linear. There's no quick fix, for example. So I want to introduce the concept, we talked about it just briefly earlier, of dBm, decibels with reference to a power level of 1 millivolt across a known impedance. So 0 dBm is the same as 1 milliwatt of power, I said millivolts, but milliwatt of power across a 50 ohm load. That's 0 dBm. And you can make measurements above this level, this reference power level, and those would be positive numbers, so that 20 dBm is the same as 100 milliwatts, 30 dBm is the same as 1 watt, 40 dBm is the same as 10 watts, 50 dBm 100, 60 dBm 1000, and 61.76 dBm is our legal output limit of 1500 watts. And we use the dB measuring system, dBm specifically, to compare power levels. And so here's above 1 milliwatt, and then below 1 milliwatt, well, we've got minus 10, minus 20, minus 30, look at minus 60. 1,000 picowatts. Woohoo! So I introduced this just to get to this. Minus 100 dBm, which is the equivalent of 0.1 picowatt, is the typical threshold for cellular radio service. That's, they say we must have a signal that's at least above that to be received. Well, you can go even lower than that. The minimum discernible signal, or aka the theoretical noise floor, is minus 174 dBm with a 1 hertz bandwidth. Very, very narrow. You're not going to actually have a receiver that can go down to 1 hertz, but we're talking about theoretical concepts here. So this is a perfect receiver at room temperature with a 1 hertz bandwidth. So it's 4 quintillionth of a milliwatt per hertz. Okay. Atmospheric noise is much, much higher than this, but all right. Note this here. So this is minus 174 dBm at 1 hertz. There we are again, right there. Now, if we double the bandwidth, we're going to actually increase the noise by 3 dB. And so if we go 4 times the bandwidth, 6 dB, or 10 times the bandwidth, 10 dB. Well, let's go with the double the bandwidth. We increase the noise power by 3 dB, and so from minus 174, we move up. Remember, these are negative numbers. We move up to minus 171 dBm. That's noise for a 2 hertz bandwidth. That's the minimum discernible signal theoretically possible for a 2 hertz bandwidth. If you want to do calculations for decibels, here is the power ratio formula. It's 10 log to base 10 of one power divided by the other power. And this log here is not natural logs, but it's log to the base 10. We're not going to have to do any of that, but just need to know these concepts. So again, here's our theoretical minimum discernible signal. We already looked at if we doubled the bandwidth to 2 hertz, then we lost 3 dB. All right, so that's minus 171. Well, consider we go to a 400 hertz CW filter. Well, using a calculator, you could do it this way. 10 log 400 divided by 1 is a difference of 26 dB. Or you can use approximation. 10 times 10 is 100, times 4 is 26 dB. So what we do is we take that theoretical minimum, minus 174, we go up by 26 dB, and so here's the answer to a test question. With a 400 hertz filter, the theoretical minimum discernible signal is minus 148 dBm. That's a really weak signal. And I mentioned something earlier about atmospheric noise being much higher than this. Well, here we are. If you look over here, here's the dBm, and here's minus 148 down below the bottom of the scale up here. And noise, atmospheric noise, this is frequency on the horizontal. So here's 5 megahertz, 10 megahertz, 15 megahertz, 20 megahertz. And you see the noise, typical noise of a quiet rural setting out in the country, or just rural setting on the dashed line here, or residential urban up on the top. And you see where the noise levels are typically, here on the Flex radio, they put in S-meter readings as well, so that noise is always going to be, atmospheric noise is always going to be much higher than minimum discernible signal, theoretical levels. Here's a little closer look at that graph. So you can use this so that if you're on 80 meters and you're in town and you see that you've got an S5 noise level, well, that's probably not atypical. There's some things you can do by getting receive antennas and whatnot to reduce that, but this is the chart, the classic chart of atmospheric noise in real life. So receiver preamp noise figures, it's the ratio in dB of the noise that is generated by a device compared to theoretical minimum noise. Of course, lower is better, and it's a useful figure of merit for terrestrial systems. So a typical low noise UHF preamplifier will have a noise figure of less than 2 dB. Just keep that in mind. A receiver's actual noise figure is the theoretical minimum discernible signal plus its own noise figure gives you the actual radio's noise floor. It's also known as a receiver's figure of merit. Oh, do I have an image problem? I don't know. You tell me. What we're talking about here are super heterodyne radios, the original style, were single conversion radios. They had radio frequency energy coming in from an antenna into the receiver, maybe filtered, maybe amplified, and then going to a mixer stage. And remember mixer math, the signal would mix with a local oscillator signal. The two original signals and the sum and the difference would be output. And if we want a 455 kilohertz intermediate frequency, we could have a 455 kilohertz IF filter there, amplify it, demodulate it, and boom, we're good. Except there are two correct solutions to the mixing. You have the desired station. This is what we're trying to receive. We have our local oscillator, which is 450 kilohertz, 455 kilohertz above the desired, so that the difference signal is going to be 455. But what if you have an interfering signal up here, 455 kilohertz above? That'll get through as well, and that's called an image frequency. One thing you can do with a single conversion superheterodyne radio, which is what we're talking about here, is you can add a pre-selector from the antenna into the receiver. And this is an additional stage of filtering, RF filtering. And so the pre-selector would help you to block the undesired image signal and any other out-of-band interference. So remember that if you've got a single conversion superhet radio, you might benefit substantially through the use of a pre-selector. And to find the image frequencies, this is how you can do it. You take the IF frequency and multiply it by 2. So in the case of a 455 kilohertz IF, all right, we get to 910. And then you add 910 to the desired receive frequency, and then that would tell you that is one possible image frequency is this, or you subtract 910 from the desired receive frequency, and the other possible image would be this. It depends on whether your radio is using a local oscillator above or below the desired frequency. All right, manufacturers said this is no good. We got to do something better, especially for communications equipment. So they came out with dual or double conversion radios and even triple conversion radios. And in this case, they have the RF signal coming in, again through a mixer. It goes up to now 50 megahertz. For the first IF, it has an amplifier and filter, and then it's down converted back to another IF, maybe 455, in a second fixed oscillator stage, and then on out. This will eliminate those image problems that we had before. So dual conversion or double conversion superhets then took over as the desired communications receivers for communications and amateur radio. How much is too much selectivity? Well, if you look on page 7-15, there's table 7.2. These are the desired amounts of selectivity we want for the various modes. So for radio teletype or digital, around 300 hertz. For Morse code, 200 to 500. These are approximations. Single sideband, 1.5 to 2.7 kilohertz. AM, 6 kilohertz. And then for VHF FM, 15 kilohertz. Why do we want to have these different filter bandwidths? And usually your radio has these selectable. Well, if you match the bandwidth to the mode, you'll get the best signal to noise ratio. We've talked a little bit about noise. There's atmospheric noise, and there's generated noise. Noise that is generated during the creation or amplification of a signal. It could be in a transmitter, or it could be in a receiver. It could be amplitude or phase noise, or something called shot noise, which are little pulses of energy. Phase jitter is a problem with local oscillators. It's a fluctuation of the output signal of a local oscillator that's average frequency is good, but it varies in phase just a little bit, rocking back and forth. And so phase jitter, you can see it here, this is kind of exaggerated, but it's something that can actually widen out the demodulated signal and cause problems, both on receive and transmit. So you want to make sure that your radio has very low phase noise or phase jitter. And phase noise is that defined as the noise arising from short-term phase fluctuations that occur in the signal. And there's a noise spectrum that is caused by this, and you can actually find it on a spectrum analyzer. Here's a ham in Germany, I believe, that actually did comparisons. This is just the upper sideband of certain types of radios. Now these are older radios now, but you can see the model numbers here as they go through. And you can see the measured phase noise of these heterodyne radios. And you see some of them are much worse than others. And that will cause problems with not being able to hear the very weakest signals. Or if it's on transmit, it will cause problems with nearby transmitters. Think field day. So you always want to have for field day, for example, radios with very low phase noise, phase jitter, so that they don't interfere. They don't cause spurious signals in the other radios. Phase noise causes false signals on either side of the local oscillator, and this can actually mix with other signals coming in the radio's passband. So I mentioned earlier that some of the older radios, like the Collins and whatnot, are still very good today. Well, they used permeability tuned oscillators, variable inductors, and they had and still have very low phase noise. And so for them, they can discern very, very weak signals that some modern radios still can't do. And so the Collins permeability tuned oscillators were great. Now, the phenomenon of not being able to receive weak signals is called phase noise masking, also known as reciprocal mixing. And if you have strong signals on nearby frequencies, they can interfere with the reception of weak signals. So here we have, I've got to put my glasses on so that I can see this. Here we have the desired signal, this very weak signal that we're trying to receive. And here's our local oscillator, 455 kilohertz above. And so we'll get an IF output, and that'd be great, except that we have this strong off-channel signal here, and a weaker but still some energy here that will mix with it on 455 kilohertz. So our own receiver is causing interference to the signal that we're trying to receive if you've got a radio with high phase noise, or this phenomenon known as reciprocal mixing. So that's one of our definitions in receiver performance. Another of those definitions is the blocking dynamic range of the amplifiers in your radio. And so if you've got an input signal coming into your radio and it's minus 50 dBm, and it goes up to a signal level of minus 40 dBm, you want the audio output, or you want the amplifier output in the radio also to track, to go up another 10 dB. But there's going to be a point at which the signal gets so strong that the radio output can't go any higher. And when it goes up, the input signal goes up by 2 dB, but you only get 1 dB increase output in the radio system. That's called 1 dB compression, the compression point. And that is the point that we classify as blocking dynamic range. And that's the radio's ability to handle strong signals, or the dynamic range of signals that it can handle. And so just remember that if you hear the term 1 dB compression, we're talking about blocking dynamic range. One thing you can do to help some of these situations is to add roofing filters to superheterodyne radios. Roofing filters come after the first mixer, that 50 megahertz IF, for example, and you can add aftermarket filters to some radios, and it will improve the dynamic range of the radio. The roofing filter goes in after the first mixer, and it improves blocking dynamic range by rejecting nearby strong signals. Something similar is desensitization. It's when a radio receiver can be desensitized, or its AGC activates with nearby strong signals. You'll see that sometimes with 2-meter radios that are nearby, and somebody keys up and your radio won't hear anything. That's desensitization. With poor dynamic range, another thing that can happen is something called cross-modulation, where 2 different signals will mix together and interfere with each other. So cross-modulation, if you've got, here's a detail you can go through when you get the presentation tomorrow, where they talk about the intercept points and some of the spectrum and whatnot, but that's cross-modulation. Another receiver specification that you'll see is the third order intercept point, and it marks the receiver performance in the presence of strong radio frequency energy. and the third order intercept point is measured by using two equally strong interfering signals, a pair of signals, that will generate a third order intermodulation product. We're going to talk about third order products here in just a little bit, equal to the desired signal level. Ooh. The two third order products of in-band signals is also likely to be in-band. We'll show you why in a second. This relates to contest performance. What I want you to remember for third order intercept point, it's a pair. A pair, you get it there? A pair of equally large signals, interfering signals that will generate intermodulation equal to the desired signal level. An intercept point is a real thing. If you've got an ICOM IC7300, for example, they added this function IP+, intercept point plus, to give the radio some additional dynamic range. All right, I have to tell you about the Bible of performance. Oh, okay. The Sherwood Engineering Radio List. Here's the URL up in red up there at the top. Rob Sherwood, ham out in the Midwest, has been testing radio receivers for years and years and years. And he has this table of radio receiver performance. It is sorted on a parameter called reciprocal mixing dynamic range, which is how well the radio would perform with close-in signals together. Very much like the CQ Worldwide Single Sideband Contest we just had this last weekend. That is not the only important parameter, however, and he'll be the first one to tell you that people shouldn't look at the list and say, oh, that's number one on the list, that's what I'm buying. You don't want to do that. He says, I'm just quoting Rob, I've seen him at Hamcation last year. He said any radio receiver on the top 25, 30 radios that are on the list, any of them are perfectly fine. He himself doesn't own the top radio. He owns two IC7610 ICOM radios, which Dave over here owns one as well. So but know about the Sherwood list and take a look at it, and you can see some of the specifications like we've talked about here. Also, I want to advise you to go look on eham.net. If you're considering buying a radio, there are reviews of amateur radio products, including transceivers and receivers, and you get practical information from people who have bought and used the radio, the things they like, the things they don't like. It'll help you out a lot. So eham.net. All right. I mentioned harmonics earlier when I was talking about non-harmonically related audio tones. So harmonics with the audio tones, if we had a 1,000 cycle or 1,000 hertz signal, its second harmonic would be 2,000. Third harmonic would be 3,000. Fourth harmonic would be 4,000. Well, the same thing exists in radio frequencies. So we talk about the fundamental frequency. We talk about the second harmonic, the third harmonic, the fourth harmonic, and the fifth harmonic. We talked about mixers earlier tonight. Remember, mixer math is such that we have an input signal here, and we have the local oscillator signal here, and you're going to get this signal, and then the sum and the difference of the two signals. All four signals will come out of the mixer, and we use a filter to eliminate that. So, intermodulation distortion products. We talked about it earlier tonight, just briefly. And we have the fundamental frequencies here. We have third order products, fifth order products, seventh order intermodulation distortion products. What the heck are we talking about? Well, all right. I'm just going to go over to the whiteboard, and I'm going to briefly try to work through this. This is an experiment. I don't know if this is going to work or not. All right, let me go over here. Let me just draw this little squiggle so I get here. All right. So what we're talking about are the fundamental Oh, you can't read my handwriting. And harmonics. That's what I wrote. Okay, anyway. So here we have two signals, and I'm going to pick some really wide range signals here. This is not practical, but this is for illustration purposes. So we've got a signal here at 10 megahertz, WWV. And we've got another equally strong signal at 10.5. All right. This is one fundamental frequency here, and this is another fundamental frequency over here. These are what we'd call the first order products. First, all right? This plus this would be 20.5, someplace out over here. This minus this would be 0.5, somewhere. Oh, yeah, can't see that. Oh, that's like I gotta. Oh, it's not going to erase. There we go. 0.5 megahertz. These signals are well away from where we're trying to receive. So they're not. These things aren't going to cause us any problems. So this is a first order. These are second order products. Third order products are 2 times this, which would be 20, minus 10.5. So it would be 9.5. Did I get that right? 20 minus 10.5. Okay, 9.5. All right, thank you. So that would put it right about in here. Well, that's pretty close. This is a third order product. And it's because it's 2 times this, 1 times this. 2, 1, that's 3. That puts it there. 2 times this is be 21 minus 10, that would be 11. Puts it right here. And we can go on and do it, but it has to do with these close-in ones here are what we call the third order products. Let's go back over here. Now this might make a little bit more sense. Oops, I'm going to go back over here. So again, the third order products are here and here. And it's the third order subtractive products that are the pesky ones, I say. So we'll show you that here in just a second. So on pages 7-17 and 18, there is this problem. They want you to find an intermodulating frequency, and they give you some information about it. So we go here, we have the intermodulation project we just talked about there. Whoops, it just jumped. Why did it do that? Okay. These are the third order products here and here. These are the ones that are closest in to our desired signals. These are the ones that we need to worry about because they're closer to our IF bandwidth. So here's the question. You're listening on 146.7 megahertz, all right? When a 146.52 megahertz signal is transmitted, it mixes with another frequency in your radio, causing interference to the signal you want to listen on. What are those possible frequencies? Oh my God. All right, so the subtractive close-in third order intermodulation products are the likely culprits. So the equations for subtractive third order are the frequency you're listening on. FMID is the frequency we're listening on, 146.7. So we can use this equation here. All right, and we get down to a new equation. I'm going to show you a simple method here in a second. Here's another way to go through it. I'm just going to jump ahead because the answers are this. 146.34 and 146.61. I want you to know about the concept of third order intermodulation products, but I don't see it of any value for you to have to do it for the test. I could be wrong, but okay. So here's what I want you to remember. 34 and 61. However you want to do it. There was a movie called 61 Star. I know that because my brother-in-law was an actor in that movie for my first wife. But 34 and 61, 146.34, 146.61, those are the possible interfering frequencies. And I went on about this a little longer in last year's class, but I'm not sure it got through any easier, so I saved you a lot of heartache. All right. FM receivers, they use something called a discriminator inside to demodulate the FM signal. You can also use a phase lock loop to do it as well, but typically they use a discriminator. And I say something about discriminators is that they only receive one signal at a time. So when two signals are on the same frequency going to the discriminator, only the stronger signal of the two signals is going to be heard. Keep that in mind. It's called the capture effect. Here's a software-defined radio. We've been talking about super heterodyne radios, but the receiving functions can be, and demodulating functions can be implemented with hardware and software. One thing we need to be aware of is the overload, though, of the analog to digital converter. The maximum signal value that a radio can receive is controlled by the analog to digital converter's reference voltage. If you go over this reference voltage, you will get something called overload or overflow. And this is the IC 7300 again from ICOM when they first came out. They did have some problems with strong signals, and you see the OVF light is lit up here. That indicated that the analog to digital converter was overloaded, or there was an overflow going on. This relates to question E4C08. And we talked about that also when we were talking about 2 to the 10th power to give us over 1,000 steps, and Dave mentioned that the ADC's reference level sets the maximum input. So here's the analog to digital converter in this radio. This radio is actually using front end here for the radio, and then the converter, and then a digital back end for digital signal processing over here. And the reference level is set, again, that's the maximum signal level that can be demodulated by the analog to digital converter. And if we look closely at one of the chip pictorials here, there is reference voltage right here and the analog voltage in. So the reference voltage has to do with the maximum signal strength, and the number of bits has to do with the smallest resolvable signal. Software-defined radios can have problems, hiccups, resulting in signal distortion. One is called differential nonlinearity, or also known as a least significant bit error. And that's where we can add noise to the signal to dither it to eliminate some of this. The SDR's dynamic range, the most important thing is the analog to digital converter's sample width in bits. The more bits you have, the better dynamic range that you will have, and also the lower distortion of the signal. We talked about in super heterodyne radios the importance of low phase noise. Well, also in SDRs you want to have low clock noise. Phase noise in the SDR clock signal can sometimes mix with nearby strong signals and cause spurious problems. So all these things the manufacturer is hopefully dealing with properly, but these are things you want to know about. Have you ever gone to a ham fest with another convoy, or another group of folks, and they're in a car ahead of you, so you're making up a convoy? Okay, I finally got there. And the guy you're all on the same repeater, you're listening to the same repeater, and the guy in the vehicle ahead of you keys up their radio, and your radio doesn't hear anything? Does that ever happen? That's desense. We talked a little bit about it before, but radios can be made deaf by strong signals in their presence. And you can actually improve this situation by either decreasing the receive bandwidth on the front end if that's possible, or even adding an attenuator. And the fix is counterintuitive, but you want less signal, not more, in order to hear the radio repeater, for example. All right, you made it through all that. Let's answer some questions. What is an effective excessive phase noise in an SDR receiver's master clock oscillator?
Delta?
It is delta. This is one of those cases, one of our students said, it's always the longest answer that's right. Well, in this case, it can combine with strong signals on nearby frequencies to generate interference. Which of the following receiver circuits can be effective in eliminating interference from strong out-of-band signals?
Alpha.
Yeah, especially for the single conversion radios, you pre-selector or front-end filter. And what is the term for the suppression in an FM receiver of one signal by another stronger signal on the same frequency? What do we call that?
Alpha?
Not alpha.
No.
Charlie.
Char.
In this case, it's the capture effect of the discriminator. The discriminator can only handle one signal at a time.
Okay.
And what is the noise figure of a receiver?
Delta.
It's the ratio in decibels of the noise generated by the receiver compared to the theoretical minimum noise. And what does a receiver noise floor of minus 174 dBm represent?
The theoretical.
Bravo.
It's as low as you can go. It's the theoretical noise in a 1 hertz bandwidth at the input of a perfect receiver at room temperature. We can't build them, but it's a theoretical concept. So how much does increasing a receiver's bandwidth from 50 to 1000 hertz decrease the receiver's noise floor?
Delta.
Delta.
Great, you got it. Yes, 13 dB. And what does the MDS of a receiver represent?
Bravo.
Yes, the minimum discernible signal. An SDR receiver is overloaded when input signals exceed what level? I heard it.
Delta.
Yeah, the reference voltage of the analog to digital converter. And which of the following choices is a good reason for selecting a high IF for a superheterodyne HF or VHF communications receiver?
Charlie.
We're talking about eliminating image responses, image frequencies, faults. And what is an advantage of having a variety of receiver bandwidths from which to select? Yes, if you match the receiver bandwidth to the mode, then you maximize signal to noise ratio. And why does input attenuation reduce receiver overload on the lower frequency HF bands with little or no impact to signal to noise ratio? We didn't specifically talk about this.
Delta.
Yeah, atmospheric noise is generally still greater than internally generated noise after attenuation, even after attenuation. So, yep. And how does a narrow band roofing filter affect receiver performance?
Charlie.
Charlie.
It is Charlie. It
Yeah.
improves blocking dynamic range by attenuating strong signals near the desired receive frequency. So what is reciprocal mixing?
Delta.
Delta.
Yeah, you don't want to have phase noise. Local oscillator phase noise mixing with adjacent strong signals creating interference. And what is the purpose of the receiver IF shift control on radios? What do you think?
Charlie.
Yeah, you had it. Yeah,
Charlie.
the controls on the receivers, the transceivers, are there to help you reduce interference. So this is one way to do it by shifting the IF up or down slightly. You might be able to eliminate nearby interference on adjacent frequencies. And what is meant by the blocking dynamic range of a receiver?
Alpha.
It is alpha. It's blocked because it can't amplify anymore. It's compressed. The difference in dB between the noise floor and the level of an incoming signal that causes 1 dB of gain compression, that's the blocking dynamic range of the receiver. And which of the following describes problems caused by poor dynamic range in a receiver?
Alpha.
Yes, spurious signals will be caused by cross-modulation and then desensitization from strong adjacent signals. And what transmitter frequencies would create an intermod product of signals in a receiver tuned to 146.7 when a nearby station transmits on 146.52?
Alpha.
Alpha.
Yeah, 3-4 and 6-1. 3-4 and 6-1. That's my cheat. So
Good
what is the term for the reduction in receiver sensitivity caused by strong signal near the received frequency? This is what we talked about earlier.
Charlie.
Charlie.
This is desense, because remember, the input frequency to a receiver, to a repeater, is going to be different than the output frequency of the repeater, so it's nearby, but it causes desense. Not on the same frequency. All right. So which of the following reduces the likelihood of receiver desense? Remember, it's counterintuitive.
Alpha.
Alpha.
Inserting attenuation. And what is the purpose of the preselector in a communications receiver? Not Bravo.
Charlie.
Charlie.
It is Charlie, to increase the rejection of signals outside of the frequency range that you want to receive. So what does a third order intercept level of 40 dBm mean with respect to receiver performance?
Charlie.
It's a pair of 40 dBm input signals that will theoretically generate a third order intermod product that has the same output amplitude as either of the input signals. And why are odd order intermodulation products created within a receiver of particular interest compared to other products?
Alpha.
Alpha.
It is. Odd order products of two signals in the band being received are also likely to be within band. And what power level does a receiver minimum discernible signal of minus 100 dBm represent?
Delta.
Delta.
Very good. 0.1 picowatts. That's the cellular level. Perfect. All right. Last section, interference and noise. We saw this chart earlier. Atmospheric noise and where you live has an impact. So your station for HF certainly would benefit from not being in the city, but being more out in the country. So the various noise levels that you might see on the various bands. Right now, with the hurricane going on down in Jamaica, there's a lot of lightning activity and whatnot. And QRN, atmospheric static, largely caused by thunderstorms. And here's a website, Blitzortung, that you can go and actually get live looks at the lightning flashes in your area, for example, while the storm is going on. So it's kind of neat to see. So that's QRN. That's natural interference. QRM, are you QRMing yourself? Is there something in your house that is causing interference to you? The number one problem will be cheap Chinese power supplies. The little wall wart power supplies, they're not RF filtered, generally. And so you'll find that unplugging the power supply to your Simply Safe security system might eliminate the noise that you're hearing on 20 meters. True story. So you can find a noise source in your house by using a battery-operated radio of some kind, listening to the noise, and start turning off circuit breakers one at a time in your house. If the noise goes away, hey, it's in your house and it's in that room. So you can go check and go look. Now, noise can be picked up on cables. Antenna cables, audio cables, etc. And when we're talking about noise pickup in this way, we're talking about common mode noise. It's a signal that is picked up on the outer shield of a coax, and it's a voltage with reference to earth, with reference to ground. The coax, when you're transmitting and receiving, the signals there are what we call differential mode. It's going back and forth with the center conductor and the inside of the shield. And so generally noise is not picked up differentially, but common mode noise is picked up. And it's a type of signal transfer from a transmitter to wiring or from a noise source to an antenna system. And the cure, ferrites are your friend. Little ferrite devices like this. Now, for HF, you probably need a bunch of these, and they need to be of a certain type. Type 31 is recommended. But putting ferrites on cables can eliminate a lot of problems. Anybody got touch lights still in your house? Actually, I have one. They're notorious for causing radio frequency interference. It sounds like AC hum on an AC receiver. It can drift slowly across the HF spectrum, and they're several kilohertz in width and usually repeating at various spots. So touch control lights are generally not good for amateur radio. Transmitters that are in close proximity with one another can mix their output signals together and give us third order intermodulation products. And they mix the outputs of two transmitters, for example, can mix in nonlinear devices or junctions. Here's the top of a communications mountain. There's a lot of intermodulation going on there. I can guarantee it. It doesn't take a lot of effort to generate intermodulation products. Intermod comes from mixing, and the practical result is that there's off-frequency, unwanted signals heard in addition to the desired signals. So if you have a transmitter on the mountaintop like that, you really want to consider using something called a circulator. It's effective in eliminating transmitter intermodulation, and it uses ferrite components that act as one-way valves. It's a 3-port device. So here's one right here, for example. It gives 30 dB of isolation with about a half a dB of insertion loss. And so the transmitter output power comes here, goes into the circulator, comes out over here to the antenna. This port has a 50 ohm dummy load connected to it. Other transmitted power from another transmitter that's on the mountain comes in from the antenna, but it goes directly to the dummy load and is not sent back into the back of the transmitter over here where intermod products would likely be generated. So this is a circulator, and it's always recommended for mountaintop installations when there's multiple transmitters. It doesn't have to mix inside of a transmitter, however. Rust The rusty bolt effect can cause two transmitters to mix passively. And nearby AM stations sometimes can be mixed up into the ham bands if they don't take care of their towers and keep the rust off. So try to make sure, that's the reason why tower maintenance is so important, not only for mechanical safety, but also to prevent intermodulation because of this. All right, moving on. Are you going to put a radio, an HF radio in your car? If you are, you're going to be fighting impulse noise. Noise that comes from spark plugs, from spark plug wiring, from the alternator. It's going to have whining and whatnot. Now, a noise blanker can help with the impulse noise from spark plugs. A noise blanker is like pulsed squelch. It eliminates the spikes of ignition by just turning off the audio briefly. Here's a noise spike here, for example. It'll mute out the radio briefly during that, and you don't hear it. So noise blankers can be very effective. Can also help you out if you're in the country with electric fences. Sometimes the noise blanker can be helpful there to eliminate that sort of a noise. But you do not want to leave it on all the time. Only use it judiciously. Only use it when you need it. Otherwise, you can cause distortion to receive signals and cause them actually to appear wider in bandwidth than they really are. Back in the vehicle, if you've got alternator whine, there are things that you can do. You can install coaxial capacitors. You can make sure you bring the radio power leads directly to the battery. And ferrites, again, are your friend. Add ferrite beads to the leads to prevent pickup. Have you got motor noise? Something in your house when the motor comes on, generates a lot of noise? Look for one of these. They're called brute force line filters. And it consists of capacitors and inductors in a case here that will actually help minimize some of the noise sources. And there's all sorts of different kinds of noise sources. You can get thermostat contacts that are arcing on the old style thermostats. That'll cause RF noise. Doorbells, their transformers can malfunction. Electric signs can cause you problems. You can cause your own problems. All right, this is not cool, but here's the story of how I QRM'd myself. So I was an earlier adopter of the Flex radio system. I wanted to know more about software-defined radios, and so my first SDR was a Flex 6500, and a beautiful radio, and it used software that would run on a PC called a Smart SDR to control the radio. And so I bought inexpensive Windows PC at a Hamfest. It was a pullout from a business or something like that that had been refurbished, and put them together. If you can go back to the laptop there, Bruce. So here's the 6500 up on top. Here's my pullout computer. It was an old Dell running Smart SDR software. But I would always have, see these kind of lines you see along in here? These line bands of noise. And I could never figure where is this noise coming from? And I'd try different things and whatnot, and I could never find what was going on. And then Flex came out with something called their Maestro. You've seen that earlier here. And I thought that'd be a cool thing to have, so I ordered one, got the Maestro in, and so the Maestro replaces the computer. You don't need to be running Smart SDR on the computer anymore. So as I was hooking up the Maestro, I turned off the computer, and the noise went away. My own computer had been QRMing my radio station, and the moral of the story is that computer power supplies can generate noise and signals in the amateur radio bands. They're unstable signals at various frequencies, and what I was able to do is, these are ferrite toroids that are stacked here in a stack of I think 5 or 6, and by wrapping the power cord through them 4 or 5 times, that would block the noise that was coming out of the switching power supply here from getting into the AC power system at my ham shack and then radiating out, and that was able to block the noise. So just know that computer power supplies can cause problems. We mentioned digital signal processing. It can be either built into your radio, or you'll see at Hamfest these outboard DSP units. This is one from Radio Shack, by the way. Just works on the audio level, but you can provide additional filtering, noise blanking, notch filtering, etc., all in digital signal processing. But be aware, if you turn on automatic notch filtering, which is designed to eliminate a carrier that might come up on frequency and cause a continuous tone, it doesn't know the difference between that and a Morse code signal of a continuous tone. And what happens if you have the DSP automatic notch filter turned on and you're tuning CW, you'll hear nothing because it's eliminating it. So just keep that in mind. Use it judiciously. Okay, some questions. So what creates intermodulation interference between two repeaters in close proximity?
Bravo?
Say again?
Bravo?
Yes, bravo. The output signals of the two transmitters can mix in the final amplifier of one or both of the transmitters. That's where you want to add a circulator instead. And which of the following is used to reduce or eliminate intermodulation interference in a repeater caused by a nearby transmitter? Oh, I think I just gave the answer.
Bravo.
Yeah, that's a properly terminated circulator at the output of the repeater's transmitter. And what causes intermod in an electronic circuit?
Charlie.
Charlie?
It's caused by nonlinear circuits or devices. And what undesirable effect can occur using a noise blanker?
Yep.
I wasn't specific about this. It is Charlie. Strong signals
Charlie?
can be distorted or appear to cause spurious emissions if you run the noise blanker. So that's why we say only use it when you need it. So which of the following can create intermittent loud roaring or buzzing AC line interference? Read carefully.
Delta?
Delta.
So arcing contacts,
Yeah.
yeah, a defective doorbell, yeah, malfunctioning sign, yeah, all of those. What could be the cause of local AM broadcast signals combining to generate spurious signals on the medium frequency or high frequency bands?
Bravo.
The rusty bolt effect. Nearby corroded metal connections are mixing and re-radiating the broadcast signals. It's a real thing. And that, ladies and gentlemen, is the end of Chapter 7. And we're getting out on time. That's great. Go ahead and remove the spotlight if you would, Dave. And are there any questions or comments before we get out of here tonight? Upper left-hand corner. There you go. Was my audio better in the second half?
Yeah.
Okay, good.
I never heard a problem.
Okay. Yeah, it could have been a local thing. I'll listen to the recording tomorrow. So
You had a little
Dave,
bit more of an event.
next week, what's up?
All right, well, next week we're going to be into Chapter 8. Chapter 8 is another very meaty chapter, and we're going to...
Do you have his mic on?
No.
Okay, now you should be able to hear me. Okay, Chapter 8 is a fairly meaty chapter, a lot of stuff in it. We're going to cover it in 2 weeks. So the name of the chapter is Modulation, Protocols, and Modes. And you may notice as we're going through these chapters that some of them build on one another. Some of the things that Gary talked about tonight were some expansions of things that I talked about in previous weeks. And that's going to be true next week as well. So to get ready for that, and I'll be sending out an email, but it starts, well, on page 8-1, and then you can read through, I'm trying to find it, through page 8-11. So 8-1 through 8-11 is what we're going to be talking about next week. And it'll probably take the full 2 hours, and it's a lot of stuff there.
Alrighty, y'all. You were great tonight, very patient. please keep the family of Charlie Wallen in our prayers and thoughts, and love those who are near you, and cherish every moment. Okay, and have fun. All right, we will see y'all next week.
Good one.
73, y'all.
7-3.
61.